An inductor is a coil of wire that stores energy in a magnetic field when current flows through it. It operates according to Faraday's law and Lenz's law, which state that a changing magnetic field induces a voltage EMF that opposes the change in current that created it. This means inductors resist sudden current changes. The measure of this opposition is called inductance, which depends on the number of turns squared, coil area, and length of the inductor, where U is the permeability of free space. Current flowing through any wire creates a magnetic field. However, coiling, like an inductor, improves field interactions, significantly increasing magnetic field strength as well as inductance. Now, let's apply this knowledge to a simple DC RL circuit. DC current is constant, and therefore there is only a change in current and therefore magnetic field when the circuit is initially turned on or off. When connected to a DC source through a resistor, initially at t equals 0, the change in current is at its highest, and therefore the EMF produced to resist the change in current within the inductor is also at its highest, and completely resists the current from flowing. This makes the current equal to 0, while the inductor behaves like an open circuit. As time progresses, known as the charging phase, the rate of current change decreases, so the induced EMF falls, allowing current to pass through the inductor and gradually increase towards the source value. As current flows through, the magnetic field of the coil increases, storing energy. After enough time, the circuit reaches steady state. This is when the current becomes constant and equal to the source current. The magnetic field is steady and no EMF is induced, in which the inductor now acts as a short circuit. When the circuit is disconnected from the power source, known as the discharging phase, a change in current occurs, resulting in an induced EMF voltage to resist this change and maintain current flow. This energy is taken from the magnetic field, which collapses, reversing the polarity of the inductor and allowing current to flow through the circuit for a short time until it decays to 0. The current through the inductor during these phases are seen in these graphs, where current is a function of time. Inversely, voltage over the inductor decreases as the inductor charges and becomes a short circuit, and increases as the inductor discharges and becomes an open circuit. It's also important to note that the total inductance of inductors in series is equal to the sum of each inductance. In a parallel connection, the total inductance is determined using the reciprocal formula, the inverse of the sum of the inverse of each inductor.